And the first thing to notice about this subject is that this is pronounced Lee and not Lie. Lee is a person's name. Sophus Lee. He was, I don't remember, Nordic, I think. Maybe Norwegian. Anyway, it's pronounced Lie algebras. So let's start with just a more general definition of Lie algebra. This is going back to just the basics of manifolds for a little bit. So for X, a subset of a vector space well, let's say it's over the reals. Now, when I say the vector space is over the reals, if you have a complex vector space, so if it were over the complex numbers, it would still be a vector space over the reals. Let's just be clear about that, right? Every complex vector space is also a real vector space. So all that's important is that there is a real vector space structure on it, because you have to know, you'll see in a second, what you need. So the tangent space at P in X. So P is a point of a subset. And that's going to be defined as follows. So it's going to be T sub P of X. So TPX, tangent space of X at P. And that's going to be the derivatives of, it's going to be the initial velocities of differentiable paths through P in X. So that's going to be gamma prime of 0 such that, so gamma prime of 0 such that gamma is going to be a curve minus epsilon to epsilon. So it's going to take this little interval around the origin. Yeah, so all it needs to be is just a little tiny bit of curve. It maps to X. And this is supposed to be differentiable with gamma of 0 equal P. Okay, so this is supposed to be, let's read what this says. We're looking at the derivatives of curves with image in X. And these curves are supposed to be differentiable so that you can actually take the derivative. And they're supposed to take 0 to P. So if you think about what the picture looks like here, the picture looks like this. So you've got some subset. Let's say here that you've got a subset of R3, let's say, right? And you're supposed to be taking a point. Let's just say that this is your point P. Okay? That's your point P. I'll draw it up there. And now what are you supposed to do? You're supposed to take a differentiable path in the sphere, right? So now we're talking about, so X is the sphere here. And so here X, that's going to be S2, and it's a subset of R3. Yeah, and we're supposed to be taking now differentiable paths through P in X. So there's supposed to be a path over here. It's supposed to go up here, and then it maybe goes through this point here, and then it kind of continues back like that, right? This is our differentiable path. What is the tangent vector at that point P of this differentiable path? It's a tangent vector, just like you think of a tangent. When you say someone goes off on a tangent, this is what you mean, right? They go up to here, and then it just sort of keeps going straight in that direction. Yeah, that would be the differential. So this is going to be, this is gamma. That's the curve gamma. And this is gamma prime of 0. Right? So this is the derivative of this curve at 0. It takes 0 to P, right? This curve is supposed to take 0 to P. So, you know, it goes, so minus epsilon goes here, epsilon goes here, or actually minus epsilon and epsilon aren't really there, but this is supposed to be an open interval. But you get the point. So now we're supposed to be looking at the set of all such possible differentiable curves. And we're supposed to take the tangent vectors of all such differentiable curves. Now, notice that here's some curve whose derivative at P is this tangent vector. There could be other curves whose derivative is also this tangent vector, right? This is not the unique curve. This is not the unique parameterized curve that goes through P, whose tangent vector is this one. But this is one. Now, if I looked at all the possible, so think about it this way. This vector is a vector in R3, right? Now, keep in mind that the origin, so when you're viewing this arrow as a vector in R3, the tail is 0, and the head is just, is the head. So the vector is really the head minus the tail, right? This is the equivalence class of arrows business. You should view this vector as starting from the origin, not as starting from P. Remember, vectors are, so when you look at this gamma prime of 0, when you write down this vector, if you want to think about what this vector is, you have to translate it to P to make it look like this. Right? This is a direction that you're supposed to be leaving P, a direction and a magnitude that you're leaving P. So this arrow, it really should have its tail at the origin, if you want to think of it as a vector. But since we're allowed to draw vectors as arrows, remember that's the head minus the tail. Okay, so this vector, whatever it is just some vector in R3. And so the point is that some vectors in R3 can be realized this way, and some vectors in R3 cannot be realized this way as derivatives, as initial velocities of differentiable paths in X through P. Right? Some vectors in R3 can be realized this way, some cannot. What is the set of vectors that can be realized this way in this picture?
A plane?
It's going to be a plane, yes, and it's going to be the plane that's kind of, it's up here like this. Like this, right? So you can look at all possible tangent vectors. So all possible vectors that can be obtained by looking at an arc through P like this. You take the tangent vector, it's always going to be in this picture horizontal, in the sense of being orthogonal to the z-axis, the way I happen to have drawn it. Actually, in this picture, the z-axis doesn't really go through this point P. The z-axis really goes through a point that's slightly lower than P. Why? How do you know that? Using your linear algebra that you've learned already. Where is the xy plane?
Can you repeat the question?
Where is the xy plane in this picture?
It's through the center of the sphere?
Yes, it's through the center, and the center of the sphere is where you think it is. This is the center of the sphere. Where's the xy plane in this picture?
Oh, it's the equator, sorry.
It's the ellipse that I've drawn here, right? It's not the line that goes across the middle, it's the ellipse that I've drawn here. So it's like this, and then like this. Yeah, so that's the x-axis, and that's the x-axis, and that's the y-axis. So the z-axis should actually come, since the xy plane is tilted toward us, that means that the z-axis should go through a point that's a little bit sort of in front of the sphere. But linear algebra tells you that this ellipse, and it is an ellipse, right? Linear algebra tells you that it is an ellipse because it's a projection of a circle. And we know that projections of circles are always ellipses. That's something that we learned in a previous unit on PCA and stuff, right? Yeah, so this ellipse is the projection of the unit circle that's supposed to be the xy plane. But because we had to tilt the sphere a little bit forward to see that ellipse, that means that the North Pole should actually be somewhere on the front of the sphere. So the point P that I've drawn here is not the North Pole. It doesn't matter, but just as a matter of, let's make sure that we get our geometry correct. Let's think about it properly. Okay, so let's do an example. Let's do this example, but in general. Are there any questions about this so far? Raise your hand if you've seen the notion of tangent space before. A few. Yes, okay. We simplified the definition by assuming that X is contained in a vector space. If we had an abstract manifold, we could still define tangent space, and it would still basically be defined this way, but you'd have to know when two differentiable curves give you the same tangent vector. Where it was because our space was a subset of a vector space already, the derivative is a tangent vector, and that tangent vector is a vector that lies in this ambient space anyway. So we know how to identify the two. We know how to say that two curves have the same tangent vector. That becomes a problem if you have an abstract manifold, and it's annoying, but you can get around it. Okay.
I'm sorry, this question is silly, but is S2 a vector space?
No.
Oh,
No,
sorry,
no, no,
it's a subset of.
But TP of S2 is a vector space. So this is TP of S2. And that TP of S2, that's a vector space. So again, this point here, inside of, so this point when viewed as being red should be thought of as the origin. When viewed as being white, it should be thought of as being P.
Mm-hmm.
This distinction is going to come up. It's really important that you should think of the tangent space as being a vector space. You can add two tangent vectors and you get another tangent vector. You can multiply a tangent vector by a scalar and you get another tangent vector. If I multiply this set of blue points by a scalar, it would move it out or in. But when I think of it as a subset of the red bit, then it just gets scaled the way you think it is. Yeah? So that's an important distinction to make. Thank you for that question. Okay. Okay, so the example is going to be x is s n minus 1 contained in R n. Now, we just drew the picture for S2 and we convinced ourselves that this ought to be a plane. How do you prove that this is actually a two-dimensional plane in R3? So what is the sphere, right? The sphere is the set of points. It's the set of vectors in R3 with length 1. Agreed? This is the unit sphere. We could do it with a sphere of different radius, but let's just make it 1 because it'll make all the calculations easier. So then, what does it mean for gamma of t to be contained in Sn minus 1? Right, so the first thing you should notice about this right-hand side of what Tp of x is defined to be has a number of things. It's supposed to say, first of all, that gamma is a path. Right? Second of all, that path is supposed to be contained in x. It's not just a path in R3 or Rn here. It's contained in x. And third, its value at 0 should be p. Fourth, it should be differentiable. Okay? So what does it mean just for gamma of t to be contained in Sn minus 1? What does that mean literally? Let's do it over here. So that means that it means literally that the dot product, if you take gamma of t, that's what? That's just a point in Rn, right? So this point is supposed to have length 1. So to say this point has length 1, that means the dot product of this vector with itself. For any fixed t, the dot product of this vector with itself is supposed to be equal 1. So let's just write that down. So this says that gamma of t, dot gamma of t is equal to 1. That's if and only if, right? That's just what it means to be inside the sphere. Okay, so what is that? What is gamma of t dot gamma of t? That is gamma 1 of t squared plus dot 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 plus gamma n of t squared, right? And so this thing equals 1. That's that implies certainly. Let me take the derivative of this equation. You know, I have this equation over here. This last one. I'm going to take the derivative with respect to t. And now you have to use the chain rule. You want to tell me what you get? Why we needed to have 222 or 212? No. Which one? What's the other one? Is it 212? Yeah. So what happens when I take the derivative with respect to t?
For each term, you'll have, so say for the first term, gamma 1,
Yep.
2 gamma 1 times gamma 1 prime.
Yep, 2 gamma 1 of t, gamma 1 prime of t, and then I can do plus dot dot dot. I get the same thing for all the others. 2 gamma n of t, gamma n prime of t. And what does it equal?
0.
0, and that's a nice thing. Okay, so how do I rewrite this? This is twice something, and what it is twice of, it's twice gamma of t dot gamma prime of t. So that's gamma 1, that's gamma of t dot gamma prime of t equals 0. That's what this equation says, right? It says twice gamma of t dot gamma prime of t equals 0. That's the same thing as you can divide by 2 since we're in a real field, 2 is not 0. Okay, and that's if and only if gamma prime of t is in gamma of t perp. Right, so what it says is the tangent space to the sphere at a point P, and now you should view this point P as being a vector like this, right? So think of that vector P, then the tangent space at P is the orthogonal space to that vector. Does this agree with the picture that we've drawn here? Yeah, we did this actually in the case of S1. If you remember when we did multiplication of complex numbers, we did sort of exactly this. This is the reason why the exponential function looks the way it looks. Because it's the function whose derivative is itself. Anyway. Okay, so that's the tangent space. Oh, so this gamma of t, that means it's in the perp space. So that the derivative is in the perp space of the original vector. So what that says is that tp Sn minus 1 is contained in p perp. It doesn't say that it equals p perp yet. All we've concluded at the moment is that any tangent vector must be orthogonal to p. Any tangent vector at p must be orthogonal to p. So how about the containment the other way? So what happens if we have a line that's orthogonal to p? We need that line to be a tangent vector to p, right? So I claim that that line is equal to the tangent space at p of, and here I'm going to do another picture in a second. So this is going to be v intersect x. And that's for v is equal to the span of L and P. So what's the picture? The picture is that I slice this sphere by a two-dimensional plane. Okay, when I slice the sphere by a two-dimensional plane, what happens is I get a circle. This is supposed to be a circle in R3. Right? So if I've sliced by a two-dimensional plane, then I get a circle in R3. Which two-dimensional plane do I want to use? Well, if this was my point P, yeah, if that was my point P, then that's the origin, that's P, and now I have my line L. What I would like to be, I've already said is sort of, I already said that the L is perpendicular, so orthogonal to P. Yeah, and the point is that now if I take the span of L and P, so this thing over here, this is going to be V intersect X is this blue thing, right? So this is V right here. It's this two-dimensional plane. This two-dimensional plane is, so I remember I've been given the point P, I've been given the line L, and I've been told that they're orthogonal. So I can take the span of those two things, that gives me a plane. The intersection of that plane with the sphere is a circle, and the circle we know how to parameterize, and we can take a tangent vector, and we know, by whatever method you like, that, that the tangent vector to a circle, that every vector that's tangent to a circle is orthogonal to the tangent point. How do we know that? Well, there are only two. So up to scale, there's only one such vector, only one such non-zero vector, and we can realize it by taking any any differential parameterization of the circle. Yeah. So this essentially reduces to a one-dimensional or two-dimensional calculation, however you want to view it. It's two-dimensional if you want to think of V. It's one-dimensional if you want to think of V intersect X, which is a circle. Okay, so we did two things. We checked that the tangent space is orthogonal. The tangent space at a point P is orthogonal to P. So that means that every tangent vector is orthogonal to P. And then we check that if you give me a vector orthogonal to P, that it is in fact tangent to the sphere at that point. Questions about this?
So, under what conditions is a tangent vector orthogonal to the original vector in general?
Okay, so figure that out. It's a great question. So under what conditions is the tangent vector orthogonal to the original vector?
I mean, I don't know if there's like an immediate obvious answer that I'm
I mean, it more or less comes down to this.
Yeah.
The sphere basically is the solution to that equation.
So it seems.
Right. And you can figure that out because again, you know, you're looking at the equation gamma of t dot gamma prime of t is equal to 0. Now you're only looking at this at actual, you know, t equals 0. So this is assuming that it's sort of constant, that gamma of t dot gamma of t is constant. And you're asking a question about a single point. Nonetheless, what it means is that the surface that you're looking at looks kind of spherical in a neighborhood of that point.
Yeah, that's what I felt, like the curvature is spherical, but I wouldn't know how to phrase it.
Now, curvature is an actual thing, and one can define actual curvature, and what it means is that it's kind of constant in a neighborhood and it's pointing in the right direction. So, yeah. So think about that, but think about that in a different course than this one. That would be for a differential geometry course. Yeah. Further questions?
How did we get the last imply?
This one?
Yeah.
This one right here?
Yeah.
So if L is orthogonal to P, given L and P, that means you've given me a line, so L here is a line. Right? So you've given me a linear subspace of dimension 1. So if you have a subspace of dimension 1 that's orthogonal to P, then that's dimension 1, and they're orthogonal. So their span has dimension 2. Right? Their span I'm calling V. So the intersection of V with the sphere is a circle in V. Is that all right? So the point that this is a circle. Yeah? And I claim that I know what the tangents to a circle are. It's a circle with centered at the origin, right? So it's this picture, right? And now here's P. And I claim that, so the point is that you're supposed to say that this line is supposed to be tangent to the circle at P. And I claim that it is because you know how to parameterize a circle.
Okay, but this is like an implicit argument that is not listed on the board.
Well, yeah, as I said, by whatever method you like, L is equal to the tangent space. So inside of a plane, I claim that you know what the tangent space to a circle in the plane is. And you can use any method you want. The point is, there are not very many vectors in this line. Yeah? And you know that all vectors here have to be orthogonal to P. And you know that this thing has a tangent vector. It has a non-zero tangent vector. Therefore, it has to be all of the line, if you see what I mean. By the way, once you have a vector, how do you know that you can scale it? If you take your parameterized path and just make it go twice the speed, then your tangent vector gets multiplied by 2. Right? So once you have a non-zero vector in L being tangent to the circle, you have all the non-zero vectors in L being tangent to the circle. Yeah, and 0 is always tangent, because you can just take the constant path that sits at P the whole time. Fair enough? Right, it is an interesting exercise to verify that this is a vector space without knowing that it was the subset of a vector space to begin with. Okay. So the purpose of this discussion, the purpose of the definition was to give you a precise definition. The purpose of this example and discussion is to tell you that the tangent space means what you think it means. If I had asked you to, given a surface to draw a tangent plane, you all would have drawn the right thing. And the point is that that's perfectly justified to draw the right thing that way. You've probably seen these things in Math 222 anyway, is that right? You've seen tangent planes to surfaces? Right, so this is not entirely new. It's just that we can do this for any subset of a vector space. When it's a manifold, it's a good thing. Okay, so a subgroup G contained in GLN of F, and this boldface F, remember, means that it's the reals or the complexes. Yeah, so we're talking about real or complex things now. That is a manifold. So you've got a subgroup that's also a manifold. Has what's called a Lie algebra. And it's going to be this weird, funky G. That is a math frac G. It's a fracture letter G. It's like if you've ever seen these old German texts, they're written in this kind of angular, blocky kind of print. That's what this letter is. So that's a Lie algebra little g. And it's going to be the tangent space at the identity of G. There are lots of cables lying on the floor down here. They're attached to stuff, so I can't really remove them. I probably just destroyed one. Let's see. So that's it. That's the definition. It's just the tangent space at the identity, right? So for example, if we take G to be U1, what is U1? That's isomorphic to O2 of R. Yeah, and actually I think it's SO2 of R. Anyway, let's figure out what it is. So the picture is like this. What is U1? Right? What's that? That's the
Is that just the circle? Because it's the orthogonal matrices and.
That's right. These are supposed to be you know, sort of complex numbers, such that when you take their conjugate transpose and multiply them by what you had, you get 1. Right. So this is lambda in C, such that lambda star lambda equals 1, otherwise known as the unit circle. Right? Lambda star lambda is the square length of lambda. So what this says is this is lambda such that their square length is 1. That's otherwise known as the unit complex numbers. So it looks like this. All right, so this is the y-axis. This is the I-axis. Okay. So then what is the tangent space? What is the tangent space of the identity? Where is the identity in this picture?
What does it mean for a manifold to have an identity?
Well, this is a group.
Oh, so would it be the point 1, 0?
Yeah, it would be the point 1, actually. Remember, this is the complex numbers. You don't have to say 1, 0. This is the complex numbers. Each point has a name. The name of this point here is 1. The name of this point here is I. The name of this point here is -1, right? And the name of this point here is -I. So the identity of this group is just 1, right? It's this group under multiplication. So here's the identity of this group. What is the tangent space of that tangent space at that point?
The I-axis.
Yeah, it's the imaginary axis. Like this, right? So G here is equal to the span over the real numbers of I, which is otherwise known as I times the reals. That's the imaginary axis. And that is written as now this fracture U1. Okay? So that's often what happens is you take the uppercase name of the group. This is an uppercase math italic name of a group. And then what you do is you lowercase it and you make it fracture, and that gives you the Lie algebra. Okay, so that means the derivative of capital italic is lowercase Gothic.
I have a question about tangent spaces.
Yes.
So I think you defined it for a subspace for a subset X in a vector space, but here you're using it on a subgroup in a group.
Yeah.
But a group,
Go ahead.
but a group doesn't have a vector space structure to it. Does it matter?
A group does not have a vector space structure to it, but GLN of F is what I mean here is that's the invertible matrices side of M and F, right?
Right.
So so if I'd written subgroup and I'd written, so I'm in a bind here, right? If I'd written a subgroup G contained in Mn of F, you would have complained that Mn of F is not a group, so it can't have a subgroup.
Okay, I see.
Right? So the point is that G is a subgroup of GLN of F, which is contained in Mn of F, which is a vector space.
Okay, got it. Thanks.
But we knew that GLN of F contained in Mn of F we knew that Mn of F is a vector space already. So if I tell you that it's contained in here, then that's good enough for it to be contained in a vector space. Yeah, I wanted to, so when I say I'm requiring it to be a manifold, I want to eliminate things like the rational numbers inside of the reals. I don't want to talk about a Lie algebra of the rational numbers inside of the reals. I mean, it turns out there isn't one because it's all zero because you can't take a curve in the rational numbers. The rational numbers are, what is it, totally disconnected? They're not discrete, but you can't draw a real path that goes anywhere. Anyway, I want to eliminate those kinds of possibilities and only talk about subgroups that are manifolds. These are called Lie subgroups, by the way. So this is a Lie subgroup. In general, one can define a Lie group to be a group that is a manifold, but you want that the manifold structure is compatible with the group structure. So I'd have to write down a bunch of axioms, and I don't want to do that. The way I'm getting around it is by telling you that it's a subgroup of GLN and a submanifold of GLN. And then it sort of follows, the other axioms follow from that. Okay. So how do you know that this Lie algebra, so Nicole was correct, this is the tangent space, but how do we know that this is the right tangent space? Okay, we know it's the right tangent space because we did the calculation for Sn, and this is just S1, right? So that is a perfectly reasonable way to say that this is the correct tangent space. But let's go back to the stuff that we did very early on in lecture 2 or 3 about the complex numbers, right? How do you realize a purely imaginary number as the derivative of a real path inside of U1? So the point is that if I take e to the it, right? So what happens if I take, let's view it as k it, and now let's take the derivative, let's take ddt of this thing, and let's take it at t equals 0. So if I just did e to the it, what's the derivative of e to the it at t equals 0? Well, what is the derivative of e to the it?
E to the it?
No, it's
sorry.
Yeah, you're saying your mind is saying.
Oh, you're in terms of t, yes, I to the it. Yeah.
I e to the it. Right? So when I set t equal to 0, what do I get?
You get I.
I just get I, which is good because that is a purely imaginary complex number, right? Now, if I had taken a different path, so I'm going to put now my k back in here that I was about to put in there. I'm going to put all my colors. Right? If I put my k back in there, then this becomes ki, right? And that's for k in R. There you go. Right? So we're just going to parameterize the circle in the usual way, but k tells you what speed you're going. Fair enough? This is the simplest Lie algebra calculation. Very good. Okay. How about G equals GLN of F? Then what's G? What's little g? Factor G. Lie algebra guy here. So by definition, it's this thing called, again, what you do is you make the name of the group into a little factor thing. So this is called little GLN. Okay? And what is that by definition? So what is this?
It's the tangent space to the identity matrix, which I can't really visualize. I'm not
Okay,
sure
yes. Yeah, so we're taking the identity of GLN of F, the identity matrix in, frankly, the n by n matrices, and we're asking if you move a little bit away from the identity in a direction that ensures that you're still invertible, then that's a good tangent vector, right? Remember, n by n matrices, that's just a vector space. So I can stand at the identity and I can say, okay, if I'm standing at the identity, can I move in this direction? Do I remain invertible? I want to know whether I stay inside of GLN, right?
I think any direction makes you remain invertible if epsilon is sufficient.
That's right. Perturbation theory, right? If I have, the matrix is the identity, then its eigenvalues are all 1. If I move a little bit, the eigenvalues can't possibly go to 0, right? The deformation of the identity matrix is automatically invertible. What that means is I can literally go in any direction that I want, and I'm still not just sort of going along GLN, but I'm still in GLN. So GLN of F, this is inside of MN. This is open. So a tangent vector to GLN is the same as a tangent vector to MN, and that's just all of MN. What that says is if I deform an invertible matrix, no matter, so this tangent vector, what is this tangent vector? And this is a really important point, right? This is an identity matrix of size n. So this tangent vector is a matrix. Right? This tangent vector A is literally an n by n matrix. Because that's what the elements of the ambient vector space are. Remember, right? N by n matrices, that's the vector space in which GLN sits. So a tangent vector to, frankly, any subgroup of GLN is a matrix. In this case, that matrix, so this is the U1 case. In this case, the matrix is 1 by 1. But nonetheless, it is still a 1 by 1 matrix. Here, the matrices can be n by n. But still, tangent vectors to the space of matrices are matrices. Tangent vectors to the space of blobs are blobs. If you have a vector space consisting of blobs, then the tangent space to the vector space consisting of blobs, those things are all blobs. Yeah.
So does this mean that if you pick a point in the interior of X, then the tangent space is the whole space?
The question that you're asking, the question that you want to be asking, the answer is yes. I'm not sure what you just asked because you said if you pick a point in the interior of X. So the point is that if X is open inside of the ambient vector space, then the tangent space at X of any point is the whole vector space. Is that what you meant?
I mean, just in general, even if X is closed, if you pick a point in the interior, then
This subset of R3 has no interior.
right.
It's thin, right? You can approach it from either side.
But I'm referring to it in the general case. That's why in this case the tangent space is not the whole space. So if you pick
that's
a
what I'm
point,
saying. The tangent space is the whole space if your manifold is open inside of the ambient vector space.
but even if even if the manifold is closed, as long as you pick a point in the interior of the manifold, then
Well, what I'm saying is if your manifold has dimension less than the ambient vector space, then it doesn't have an interior point. The answer to the question is yes. If you pick an interior point, then the tangent space is the whole space. But your manifold doesn't have an interior point unless it locally is the whole space.
I see. Okay.
Right, so the technical answer to your question is if you manage to pick a point in X that's in the interior of X, then yes, the tangent space at X, tangent space of X at that point is the whole vector space. but the only way you can have an interior point to begin with if X contained an entire open neighborhood of that point in the ambient vector space. So the picture is like this. If you've got your space, if this is your vector space V, and that's your manifold X, then this point is not interior to X. If you know that at this point in X, you have, that this point is interior to X, that means that you've got an open ball of V that's still contained in X. And then yes, the tangent space at that point is all of V.
Yeah, that makes sense.
Yeah. Okay, let's. So these, yeah, go ahead.
Oh, sorry, I was going to ask another question. It's true that the tangent space is a vector space, right?
Yes, it is.
Yeah.
And you can try to prove that directly from this definition. It's not
right.
hard.
So in the way that we define the tangent space for the Lie algebra for the general linear group, didn't we rely on the fact that we couldn't scale it too much? Or
scale? No, you can always draw your paths faster and faster. So you can scale by anything you want.
So are we thinking of like the identity? You can take any path, and then you can scale the identity by any amount. And
no,
then
no, I don't. I want to take the path, but I just want to change the parameterization. So look at what this k does. E to the kit, it's still contained in the circle. I haven't now expanded the circle to be a bigger circle. I'm just going around this circle faster.
So it just seems like you couldn't take it if you took too big of a matrix, then you wouldn't be in the general linear group anymore.
You see what I just circled?
Yeah.
I don't have to take, I only need to take a minus epsilon to epsilon. So what this says, I'm standing at the identity. If you give me a line that's supposed to be tangent, or a big long tangent vector, I'll take a very short path that's parameterized very fast.
Then wouldn't it not be closed under scaling, not be a vector space, or am I not?
Again, because I can change the epsilon for the path. So if I want a path that's 10 times as fast, I can take an interval that's 10 times that's 1/10 the length.
I see. So okay, so yeah, because we're considering all paths through that point, right?
Yes, considering all paths, and those paths can be sort of arbitrary. They can be parameterized by intervals that are arbitrarily small.
Okay.
And you can make this path. So if I take epsilon to be 1/10, and if I go at speed 10, it will still remain invertible.
Okay, that makes sense.
It's a straight line in that case, but yeah. So by the way, this is a vector space if X is a manifold. If X is not a manifold, this doesn't have to be a vector space the way I've defined it. Like if I just take a union of two lines like this, then the tangent space there you'll find is basically going to be this thing union that thing, which is not a vector space. So X needs to be a manifold. When your manifold is a Lie group, we're gonna it's a lot easier to prove that the tangent space is a vector space. You need to know certain things about manifolds to show that it's a vector space. But I mean, you can more or less verify it chart by chart. Tangent spaces behave well with respect to taking charts, but I don't want to get into that.
I have a question. Like in that example,
So which one?
In the example, like U1, O2.
U1.
Yeah.
Okay.
So U1, you mean it's a point at 1, right?
So the audio is unclear. Say it again.
So U1 you denote it as the point 1 on the complex plane.
No. U1 is the whole circle through 1 on the complex plane. U1 is the circle.
Okay, I see. So you choose 1 as the point you want to compute the tangent space, right?
I don't choose it. That's what the definition says to do. 1 is the identity of this group. It has been chosen for me. This group has a unique element called the identity, such that this thing times anything else gives you the anything else you started with.
Oh, I see.
It's a subgroup, and a group has a unique identity element. So this is well defined, right? There's a unique identity element in here. It's the identity matrix because it's a subgroup of a matrix group. So this is the identity matrix. This is the identity 1 by 1 matrix.
So the result is all the pure imaginary numbers. That's still
Yes.
U1?
That's the U1 here. That's this, yeah.
So U1, okay. I may miss the point. Why all the pure imaginary numbers equals to U1?
We will explain this actually. We'll compute the Lie algebras of bigger matrix subgroups, but we need some technology to do that. But all the ingredients are here. Like, what did we use to do that? Well, we wrote down sort of how to do things for spheres. We wrote down this exponential map over here, right? So we're going to use exponentials and the fact that G is contained in GLN, the tangent space of all of Mn. We're going to use these facts to compute more Lie algebras. But we need more technology.
Okay.
Or some of the technology you already know, but I'm going to remind you of, because you might not know certain things about it, and some people might not have had a full presentation of it, and so on. So the next thing I want to do is to talk about exponentials. Raise your hand if you've seen it. Raise your hand if you've seen exponentials, matrix exponentials. Raise your hand if you're comfortable with matrix exponentials. Yeah, okay, that's kind of what I thought. That you've seen them, but okay, let's do it again. Let's do it again. So definition. So a matrix A in Mn of F. Again, this is the reals of the complexes. It has matrix exponential. And I won't always say matrix, it's just the exponential. And it's going to be written XA. The reason to write it XA, we will also write it as e to the a, but I need a name for the map. The map is called exp, but I will also write the exp of a as e to the a. You'll see we need the name of the map at some point. So that's going to be the identity plus a plus a squared over 2 factorial plus a cubed over 3 factorial plus dot 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 plus a to the k over k factorial plus dot 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 like this. This is a power series. This is a convergent power series, and that is something that I will not go into detail in this class, in the sense of the convergence. We're going to talk about this thing all the time for the next lecture or two, but I want this, I don't want to have to talk about the convergence issues. So the convergence issues are there. So what is this? This is, if I cover up all but, let's say this term, so if I cover up all but the first 3, this is now a matrix. This is an actual matrix. I can write it down, right? If I cover up all but the first 4 terms, it's a matrix. If I cover up all but the first k terms, I get a matrix. That sequence of matrices converges. How do you tell that that sequence of matrices converges? I mean, you check. And how do you check? You often check using norms, and you show that the norm is absolutely convergent in this sort of thing. The point is, if you look at the entries of these matrices, the entries of these matrices converge. And it's because the entries of a matrix to the k divided by k factorial is very large compared to any polynomial. So that means the entries of this matrix are very small. So the norm of a to the k over k factorial is very small, no matter which choice of norm you use. Yeah, that's basically what's going on. I don't want to get into detail about convergence issues, but suffice it to say, they are there, but because these are exponentials, which have a really nice, very, very convergent power series, Taylor series, whatever, it makes the convergent stuff easy to check, but you still do have to check it in principle. We're not going to. We're going to assume that all the convergence works. If you ever have a question about convergence issues, just raise your hand and ask, and I'll wave my hands in the appropriate way to tell you what you're supposed to do. Okay, so that's the matrix exponential. And now we have some properties of this thing. So first of all, if you take a path, gamma, from R to the n by n matrices, if you take the gamma of t is equal to e to the ta. So think of what we're doing now. We're starting off with the identity. We're going off in a direction A, and now we're exponentiating in that direction. Okay? So think of that as the same thing here, as starting at the identity here, and we're going up along a tangent vector, and we're exponentiating along that tangent vector. We're going to get a curve. Okay? That is, for each fixed real number t, you're getting e to the ta, which is a matrix. So when you vary t, you're getting a family of matrices parameterized by t, which is a real number. Okay? This is differentiable. And what's its derivative? If you were a first grader looking at the pattern matching here, what would you think the derivative would be? When you took the derivative of e to the t, when you took the derivative of e to the it, you got I e to the it. When you took the derivative of e to the kit, you got ki e to the kit. Now we're going to take the derivative of essentially a times t. What do you think the derivative should be?
A e to the
It
ta.
should just be a e to the t, a e to the at, t a, which is the same thing, by the way, as e to the ta times a. You have to be careful. Remember, matrices don't commute necessarily. This one does. So e to the ta commutes with a. Is that obvious? Well, we'll see in a second. So what this says is that gamma prime of t.
Oh, it's because a commutes with itself.
This is a gamma of t, which is the same thing as gamma of t times a. Say again?
Is that because a commutes with itself? And so if we just multiply a into that thing, you end up with a bunch of copies of a.
That's right. This thing is going to have some extra t's in it, but a commutes with t as well. I want to leave that picture up because it's too pretty to erase. I might want to talk about it again, who knows. So let's just write down the proof. And the proof will actually explain why this is true. Some proofs just prove that it's true. Some proofs actually explain why it's true. This one explains why it's true. So what is e to the ta? So we're going to term-wise and entry-wise differentiate. So e to the ta, what's that? That's I plus ta plus t squared times a squared over 2 factorial, right? Plus dot dot dot, e to the k, and then a to the k over k factorial, plus dot dot dot. Okay, so then what's e to the ta prime? So that's the derivative with respect to t, right? So that's going to be 0. This one's going to give me a, right? The derivative of ta with respect to t. Remember, a is a matrix. All of its entries are multiplied by t. You take the derivative, it's just going to give you those entries back. Yeah, so an entry of ta would be like t times a11. The derivative of t times a11 with respect to t is just a11. What happens when you do this one? Well, you're going to get 2t divided by 2 factorial, which is going to be that's going to be t over 1 factorial. So that's going to be t. How do I want to write this? It's going to be plus t times a squared. What's the next one going to give you? It's going to give you t squared over 2 factorial times a cubed. Plus dot dot dot, plus, and here we get t to the k, but it's going to be multiplied by a to the k plus 1 divided by k factorial. Right? So forget about the a's for the moment. All that's happening is that the t's are going down in 1 and canceling 1 off of the denominator, canceling the top thing off the denominator factorial. So this should have been a to the k plus 1 over k plus 1 factorial, but you reduced the t by 1 to get t to the k, and you reduced the factorial by 1 to get k factorial instead of k plus 1 factorial. So what's that? That is just So now let's factor out a copy of A. So the point is that now this is an A, but we want it to be an I. This is an A squared, but the power of t was 1, so we want to remove one of the A's. This is an A cubed, but we've got t squared over 2 factorial, so I want to remove one of the A's, and so on and so forth. This is literally A times e to the ta. It is also, by the way, equal to e to the ta times A. There's sort of nothing else to check. Now, when I did all of this, I told you there are convergence issues. I have to know that I'm allowed to differentiate this thing term by term. And that comes down to the fact that these series are all very convergent, and so you can do that. There's this analysis that you have to know to be able to do this, but just trust me that the analysis works out. And it's not like the analysis works out with lots of hard work. It's very easy. It's just not something I want to deal with right now. Okay. So the example to keep in mind is the one that I just erased. It's really this one, right? I'll just draw it up here again. So when you exponentiate, you get this path, and the tangent vector is the matrix that you started with, right? So in real Lie groups, the paths sort of go outward because exponentials get big. In complex Lie groups, right, there's you can go along when you exponentiate something imaginary, you kind of go in circles. When you exponentiate something real, you kind of go outward, right? If I had exponentiated this, then what I get is that thing. Right? So the exponential goes sort of out in real directions and around in imaginary directions. That's a picture that you should have in mind for the rest of your mathematical or physical career. Imaginary numbers exponentiate to circles, and real numbers exponentiate to rays. Really, really important to remember this geometry. Okay. Here's a fun one. If we're talking about a Swedish rock group from the 70s or 80s, ABBA. So if AB equals BA, then E to the A, E to the B is E to the A plus B, which also equals E to the B, E to the A, but that's sort of obvious because these things commute and back commutes, right? A plus B is the same as B plus A. So I don't have to write the others. Okay, proof. The binomial theorem. What does the binomial theorem say? What is A plus B to the K over K factorial? Right? Remember, look at this. I'm going to be writing the exponential of this, which means that I'm going to be writing A plus B to the K divided by K factorial. What is A plus B to the K divided by K factorial? What does the binomial theorem say? It's going to be a sum, yes? And what's the sum look like? You remember that?
A to the K plus, oh, you want that. So it's K choose R of A to the R.
Let's do it in form first. It's going to be a sum. It's going to be sum over all the I plus J equals K, right? Because we need to take A to the something, A to the I, B to the J, right? It's going to be sum of these terms with certain coefficients, right? They're trying to say, Eric? Now the coefficients are various binomial coefficients, which are something choose something else, and they're factorials divided by other factorials. Well, the binomial theorem becomes much simpler when you've divided the whole thing by K factorial, because now what happens is you just get I factorial here and J factorial there. This is the simplest form of the binomial theorem. You can check, it says exactly the same thing. This is just your usual binomial theorem divided by K factorial. And so what's the point? So these are the degree, so these are the degree k terms of, so here we have this is e to the a plus b, and here this is e to the a, e to the b. Right? How do you get a degree k term in the product of e to the a and e to the b? You have to choose you have to choose I of them from the a side and j of them from the b side, as long as I plus j is equal to k. And so it literally is this. There's sort of no guile here. This is just you write down what the product of e to the a is. So you write down what e to the a is, you write down what e to the b is, and then you just see how do you get a term of degree k there, and then you just check that you have to take a term of degree I here and a term of degree k minus I over here. And nothing else is happening. You do need these things to commute because you need that it doesn't matter what order you take them. You need for e to the a plus b, when you write this thing down, you're going to end up with a, b, a, b, a, b, a, b, a, b, this sort of thing, right? When you take powers of a plus b to some power is going to be, it's going to be something that involves an a and then a b and then some a's and some b's and some a's and some b's, and you want to be able to move the a's to one side and the b's to the other side. That's the reason why you need them to commute. So the expansion of this one is the reason why you need the AB equals BA. That's all. It's just, again, another formal thing.
Professor Miller,
Yeah.
is this if and only if?
The answer is I don't know, but my guess is it probably is. But I just don't know. I'd have to think about it. The question is, can you find two matrices that don't commute, but nonetheless e to the a plus b is e to the a, e to the b? Oh, maybe not. You might be able to do something with nilpotent matrices that makes a bunch of the products, a bunch of things zero. So if enough of these things are zero, then it'll still work, but that might force them to commute actually. So I still don't know. But if I were going to try to find a counterexample, I would try to find one using nilpotent Jordan blocks. Okay, let's see. So corollary, it says that the exponential map, and here we need the name of it, it takes little g, l, n of f to capital G, L, N of f. And of all the things you see in the course, this is probably one of the most fundamental. The exponential map takes the Lie algebra to the group. It's a way of taking a tangent vector at the identity and ending up with an actual element of the group. What's the proof, by the way? What's left to be proved? Right? We know that the exponential map takes every matrix to a matrix. Right? The question is, if you start with a tangent vector at the identity, then you end up with an invertible matrix. Yeah, so what this says, remember, little gln, I'm thinking this is, as an object, you've seen it before. This is just all n by n matrices, right? This is the Lie algebra of capital GLN. This is all n by n matrices, and this is just the invertible ones. So somehow you can start with all n by n matrices, and you get, then you get only invertible ones. Okay, so how does that happen? Well, it's because the e to the a, e to the minus a, note that a and minus a commute, right? And if I take b equal minus a, then these things commute. A times minus a is the same thing as minus a times a. So what is e to the a, e to the minus a? It's e to the a minus a, which is e to the 0, which is the identity. So the point is that the exponential of a matrix is always invertible. That's all we're checking here. Okay, now we're going to want to do more examples, And if we want to do more examples, first we needed the generalization of the exponential map. And now we need to check things about what happens near the identity when you take, okay, what kind of groups are we going to be looking at? We're going to be looking at groups, subgroups of GLN. Subgroups of GLN are things like this, like what SLN, the matrices whose determinant is 1. Or you can look at orthogonal groups or symplectic groups or whatever. A lot of these are defined by determinantal conditions. And so we need to see how exponentials and determinants interact. So here's the theorem, which we'll start to prove this time. It might not finish. It says that the trace is equal to the derivative of the determinant in the following sense. So what I mean is that dt at t equals 0 of the path that is the determinant of gamma of t, and that I claim is equal to the trace of gamma prime of 0, and that's if gamma of 0 is equal to the identity. What that says is if you have a path, remember these paths where gamma of 0 is the identity, these are the differentiable paths that you use to define the tangent space, to define the Lie algebra, which is again the tangent space of the identity, right? So this kind of gamma is the kind of gamma that we're using to define the tangent space of the identity. And the point is that if I take the determinant of that path, what is that? The determinant of that path, that's now a sequence of, well, numbers, elements of f. They're all complex numbers. So this is now a path of complex numbers, right? If I take gamma of t, that's going to give me a bunch of matrices along a path. And now I'm going to take the determinants of all those. That's going to give me a complex number for each t. It's going to be the determinant of gamma of t. That's a complex number for each t. And the point is that this path of complex numbers, I claim, is the trace of gamma prime of 0. Gamma prime of 0 is a matrix, right? That lies in Mn of f. So this is just a single matrix. I can take its trace, that is a complex number. Or I can take this path, I can take the determinants of all the matrices in this path and take the derivative of those determinants, and that's going to give me that number that appears over here. Okay? Said in short, the trace is the derivative of the determinant. What do you know about the trace and the determinant that should tell you that this is plausible?
The determinant is, well, they're both coefficients of the characteristic polynomial.
Are both coefficients of the characteristic polynomial. One is the sort of the n-1 coefficient and one is the constant term. How do you express those in terms of eigenvalues?
Oh, so yeah, the determinant's the multiplication of all the eigenvalues, the trace is the sum, I think.
Yes, this is the product of the eigenvalues, right? Determinant is the product and trace is the sum. So what we're saying is the determinant of a product is a sum, more or less. That's beginning to be plausible. So let's start by writing this part of the proof. Let's just suppose that gamma of t is a path in the n by n matrices. And let's suppose that it has distinct eigenvalues. Lambda 1 of t, lambda n of t. Okay, in C, and that's for t not equal to 0. Let's just suppose that these things have distinct eigenvalues. So how would I write that? I would say that the size of the spectrum of gamma of t is equal to n. That's a way to say that it has distinct eigenvalues, right? It says that the set of eigenvalues of gamma of t That's what this means. This lambda is the spectrum of. This set has n elements because none of them are repeated. So it's got n elements. That's a shorthand for this matrix has distinct eigenvalues. I mean, it's a shorthand that's completely precise. It's a very short way to write it, but not very many strokes of the chalk. Okay, so then.
I have a question about that.
Yeah.
When you say it has distinct eigenvalues, do you mean the functions, these n functions are distinct, or do you mean they're distinct for every single t?
It's the same thing. So why is that the same thing? So you're saying, so if you have that the gamma of t has distinct eigenvalues, then if I wiggle t a little bit, then by continuity those eigenvalues wiggle a little bit, and I couldn't have switched any of them. So I know what the first one is, and the second one is, and the third one is, and so on. Right? So if I just take any t, and I say, okay, let me just take the first one, let me just put them in order. Then if I wiggle t, then I'm going to know, so so if I look at gamma of t versus gamma, so gamma of t naught versus gamma of t1, then this has n eigenvalues. This has n eigenvalues. And the point is that there's a matching between them, but I know which one corresponds to which. Because if t naught is close to t1, then I couldn't have switched any of them by continuity. Right? Because they're sitting sort of in the complex plane like this. If I wiggle t by just a little bit, these eigenvalues stay in their own little disks, and I just have to tell you which disk it is.
Right, that makes sense.
Yeah?
Yeah.
Good, so this hypothesis of distinct eigenvalues tells you that I can follow them like this. Very important about distinct eigenvalues. Distinct eigenvalues is nice, because it's not just diagonalizable, it's distinct eigenvalues. This is a hypothesis, by the way. This is a real hypothesis. Distinct eigenvalues is a non-trivial thing to assume, but it makes the proof much easier. And then we'll do it first. So today we'll do the proof like this because it's just another line. And then we'll reduce to this case next time. And reducing to this case uses perturbation theory, which is why I did perturbation theory first. Okay, so then, over here, what is the determinant of gamma of t? That's going to be lambda 1 of t product up through lambda n of t. So that implies that the determinant of, well, let's do it this way. Prime, I've just taken the derivative of both sides with respect to t. And now what does it do? It's going to change this product into a sum. How's that going to work? Well, it's the product rule, right? So this is now going to be equal to the derivative of the first times, oh boy. So now what it's going to be is it's going to be this thing divided by that one. So I'm going to now cross out the lambda 1 of t business. Sorry, it's lambda 1 of t prime times, and I claim that it's this, it's going to be the determinant of gamma of t divided by lambda 1 of t. And then plus dot, 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 and now it's going to be lambda n prime of t times the determinant of gamma of t divided by lambda n of t. What you're doing is you're taking the derivative of the ith one in turn, and when you do that, you just sort of leave the rest of them. So what you're saying is take this product, cancel out the first term, but make it a derivative instead. Right? So we want to take this product and we want to make the first one into a derivative, but leave the rest of them the same. The way to do that is to make the first one into the derivative and then take the whole product and divide out by the first one. Fair enough? So what is that now? If we take, if we take this and evaluate it at 0, so we take det prime, gamma, and now plug in 0 to this thing, what we're going to get is I'm just going to evaluate this expression at t equals 0. That's literally all I'm doing is evaluating this expression at t equals 0. This is going to give me lambda 1 prime of 0 times, now, what is this expression evaluated at 0? What was our hypothesis? So you're all muted, so anybody who's saying anything I can't hear.
It's
What?
that gamma of 0 is the identity, and the determinant of the identity is 1.
Yes, and what's lambda 1 at the identity, at 0?
Also 1.
Also 1. All of these things are 1. So this is just times 1. Lambda n prime of 0 times 1, which is what we wanted. Fun? Okay, so we're going to stop the proof for the moment. So we're going to pause here until next time. The point is that the derivative of the determinant is the trace of the derivative. And that's because the derivative process takes this product of eigenvalues into a sum of eigenvalues. And all the other stuff goes away because we made an assumption about what happens at t equals 0. At t equals 0, the path itself is the identity, and that makes everything else go away except for the little derivatives of the eigenvalues that we were caring about. Okay, so next time we will continue with the proof with the reduction from the general case to the case of distinct eigenvalues. And again, we're going to use continuity again. So perturbation theory is coming up here in this proof in some kind of essential way. There are ways to prove this without perturbation theory. You can make a direct check by expanding using cofactors and all, but the notation is very ugly and it doesn't explain why it's true. This really explains why it's true. And you just have to sort of try to make this proof work when the eigenvalues aren't distinct. What you do is you just move the path a little bit so that it has distinct eigenvalues and then take the limit as the path goes to one you're interested in.